Okay, hello everybody. Mr. Lau back here again. So today we will carry on with the second set of lecture. So this time around, what we are going to do is we are going to introduce statistics itself. Okay, some of you might have already started learning in school. Okay, but I hope you can take a few minutes to listen to what I got to say first. Okay, and hopefully you can adopt my thinking and my ideology for statistics itself. Okay, so for this first chapter, what we are going to do is we are going to introduce statistics, and particularly using this discrete random variables. Okay, so actually what is statistics? Okay, for those who have learned it already, you might have already heard that statistics also involve probability. Okay, but is statistics and probability the same? Okay, are they even the same thing? Okay, because previously the last week, okay, we actually learned about probability. Okay, so the probability that we learn over there, okay, is actually theoretical probability. Okay, so let's recall the theoretical probability formula. Okay, so let's the theoretical probability formula. Okay, let's call it theoretical. Is actually the required outcomes over the total outcomes. Okay, so this theoretical probability is actually a set of theoretical results. So for example, okay, in a coin toss, what's the probability of getting a hit? All right, so the required outcome is actually 1, and the total number of outcome is 2. So theoretically speaking, flipping a coin gives you a 0.5 chance of getting a hit. Okay, then what is statistics? So statistics is actually an area of study whereby we use data to churn out a set of probability. Okay, I say again, we use data to churn out a set of probability. That means to say that the experiment must be conducted multiple times. So if I use back the same example, the coin toss. So for example, if let's say I let n be the coin toss, number of coin toss, if today n is equal to 10, so if I flip 10 coins, so I can say that statistically, the probability of getting a hit, okay, because this is an actual experiment, so if you do it at home, okay, depends on your luck, you might say, okay, probably it will give you maybe 4 out of 10. That means out of the 10 coin toss, 4 give you head, the other 6 give you tail. So statistically, when you throw the coin 10 times, the probability of getting a hit is 4 out of 10. So what if I continue to increase the number of coin toss? So let's say I increase it to 1,000. Let's say now it's semi-lockdown, right? Everybody's at home and nothing to do. So if you really want to prove it to yourself, you can stay at home and toss the coin 1,000 times. So in this case, if I toss a coin 1,000 times, okay, so the probability of hit, okay, will be, okay, very close to 500. So for example, it might give you 498 out of 1,000. Okay, so you see that as the number of coin toss increases, the probability gets closer and closer to half. So what is the extreme limit? The extreme limit is when n is equal to infinity. So when you toss the coin infinite amount of times, okay, then we can say that the probability of getting hit will be equals to half. So what's the difference between statistical probability and theoretical probability? Theoretical probability is based on theory, based on a fair, unbiased theory. But statistical, okay, we basically use the data. Okay, we collect the number of frequencies, the number of times something happen, and then we churn out the probability. And we can safely say that if I conduct it infinite amount of times, okay, the probability, the statistical probability will be equals to the theoretical probability. Okay, so therefore, okay, that's the difference. Hopefully everybody can see. Okay, so in the area of studying statistics, okay, the first most important thing is we can see here is actually to do data collection. Okay, some of you might have done your project work, okay, PW last year. Okay, so you might have already gone through this step of collecting data. Collecting data of interest, for example, the number of people who like to drink bubble tea, the number of people with height more than 200 cm, the number of boys within a school. Okay, these are interests of data depending on what you are studying. Number two is, of course, to analyze the data. Okay, collecting data, crudely speaking, is any man's job. Anybody can do it. Just give it a task. The person take a pen and paper, he can go and collect data. Okay, but as an academician or as somebody who has studied, you must value add it. You must be able to analyze the data. Okay, we can analyze data using simple parameters. For example, like the average value. What is the average value? Correct. We take all the data and divide it by the total number of surveys that we do. Or what is the mode, which is the highest occurring value. Okay, so these are some examples of parameters that we can calculate, which serves as an analysis of the data set. Then after that, we will try to interpret the data, number three, and try to feed it into an existing probabilistic or statistical model. Okay, so once we have this model will come in the form of a mathematical equation. We will look at it later on. Okay, number four is actually to apply the identified model to predict the probability of future events. So that is where the essence of statistics lies. Okay, being able to use a set of historical data, and then we use it to predict that, oh, the probability of it going that way or this way has this amount of chance based on previous data. For those who are interested in stocks, for those who are interested in equities, okay, this is an area whereby you can earn money. Okay, we can use technical tools. Okay, these technical tools basically helps us to analyze the past data of whatever stock that you're looking at. And then you can use it to predict whether the next move will be a buy call or a sell call in the event whereby you can earn money out of it. Okay, but that's not within the topic. Okay, so for our study, in this case, we actually shall focus only on step 3 and 4. Of course, we are not going to ask you guys to go out there and collect data. Okay, we are just going to interpret the results, try to work out some parameters and fit it into a model. Okay, for our H2 syllabus, we are going to learn 3 models: a uniform distribution, binomial distribution, and also your normal distribution. Okay, so once we do step 3 and 4, we can use step number 4 to churn out the probabilities of future events. Okay, so for this chapter itself, which serves as an introduction, okay, firstly, we must understand what is the structure of random variables. Secondly, we apply statistical relationship to discrete random variables. And lastly, we try to solve some questions so that we can ace our A levels, right? That's the objective. Okay, Ken? All right, so the next page. Okay, so over here, we want to talk about the framework. Okay, we want to talk about the framework of this statistical studies. Okay, so previously when we work out probability, okay, we usually use the notation like this: probability of getting a hit, probability of getting a sixes in 6 die throw, probability of getting a rain in the morning. Okay, but what we want to do here is to simplify things. So instead of writing in English, I hate English. Okay, what we can do here is to assign a random value to each outcome. Okay, this framework helps us to solve statistics questions easier. Okay, so for example, if we have a 2 coin toss experiment, we will assign the following numbers to the outcomes or events. 1 is getting 2 hits, 2 is getting 2 tails, 3 is getting 1 hit, 1 tail. Okay, so therefore we can say that the outcome takes a random value. Okay, it can be 1, 2, or 3. All right. So if we let the outcomes take a certain value, so x itself is defined to be the outcome. So instead of saying probability of getting 2 heads, we can just say px equals to 1. Instead of saying probability of getting 2 tails, we can just say px equals to 2. And of course, px equals to 3. All right, so we don't use English over here. Instead, we use a numerical value, okay, which we call a random value. Okay, next. So we have actually successfully introduced the idea of a random variable. Okay, so basically it's just an algebraic expression of a certain event. Okay, so this random variable can be categorized into 2 types, which is our interest for this H2 syllabus. The first one is actually DRV. Okay, DRV is discrete random variable, meaning to say that the random variable can only take discrete values, values like 1, 2, 3, 4, integer values. Okay, using just another example, the number of coin toss, so px equals to 1, 2, 3, 4, 5. So this is an example of a discrete random variable. Another example that we want to look at is continuous random variable, CRV. So CRV, for example, is the length of iPhone produced by the machine. Okay, because for every machine, we can't basically be producing things of an exact dimension. Okay, there's something called the deviation, there's something called the variance. Okay, there's certain machine settings that we can keep it within range, within bound. So in this case, this is an example of a continuous random variable, because if we are talking about the length of an iPhone, okay, it can be py equals to 15, 15.1, or 14.7, and so on and so forth. So there's a decimal place, it's not integer values, it's continuous. Okay, and so 2 types. So as I mentioned just now, when we do some analysis, we hope to summarize the data of my experiment. Okay, so there's 3 important parameters that we wish to summarize for at least for our syllabus. Okay, in fact, for most of the postgraduate studies, we mainly make use of these probabilistic studies. And we are looking actually at these 2 main variables. One is your mean, which is the average, common sense. It tells you the average value of your data. And the other one will be your spread of the data. Okay, sigma square is the variance. It's considered the spread of data. It actually measures how wide your data is being spread out. Okay, so what is the importance of variance? So for example, if I have 2 teachers, I have teacher A and teacher B. Okay, so for teacher A, he claimed that the average value for his mathematics exam among all his students is actually 80 marks. For teacher B, he or she claims that the average mark is actually 75 for his class. Okay, but is this average value alone able to tell us how well their students perform? Can I just based on this value alone say that, oh, no, teacher A students are better than teacher B students? The simple answer to this is no. Okay, so what if I tell you that teacher A has students who score values ranging from 60 to 100? And instead, teacher B has students who score only range from maybe 74 to 76. So we can see that the spread of teacher B is actually smaller. That means most of their students from teacher B is actually performing around the average value compared to that of teacher A, which has a wider spread. So that is the significance of variance. It tells us the spread of the data. So sigma square is the variance. If you take the root of it, sigma is called the standard deviation. Okay. Of course, the last parameter that we look at is actually the mode, which is the value of the highest occurrence. Okay. So now we are done with the formatting. Okay, so remember, for statistics, what we are interested in is to assign a random value to an outcome. Okay, so this format or this framework help us to study probability or statistics itself better. Okay, now next, let's move on to number 2, analyzing the data. So for discrete, so for this chapter, we are going to focus on discrete random variables. Okay, that means to say that the random value will only take discrete values. All right, so most of the time, the data, okay, is presented in the table format, like in here. Okay, an example would be like this. So when x equals to 1, the probability is 0.1. X equals to 2, probability is 0.2. X equals to 3, probability is 0.3. X equals to 4, probability is 0.4. Okay, so what are some of the formulas or some of the characteristics of such a data? Okay, so using this same example, let's take a look. What if I add up all the probabilities together within this set? Okay, it actually gives us the value 1. Okay, so when I talk about this set, means that everything, all the possibilities are already here. 1, 2, 3, and 4. X equals to 1, 2, 3, and 4 are all the possibilities. There's no other stuff. So if this is within the same universal set, all the probabilities must add up to be equals to 1. Okay, so if you were to write it mathematically, okay, in this case, using the same example, so what we have done here is px equals to 1 plus px equals to 2 plus px equals to 3 plus px equals to 4, and this value should give you 1. All right. So we can come up with a neater expression by using the summation sign. Okay, so the summation sign of px is equals to xi must be equals to 1. Okay, so this will be the first relationship that we are looking at. So under the same universal set, if I sum up all the probabilities, it should give you the value 1. Okay, let's move on. Next, let's calculate the mean. Okay, so the mean is actually the average of the values, or sometimes we can call it the expectation. So how do we actually calculate the mean value? In this case, if you look at the example, we can calculate the mean value, okay, by using each of the random variable multiplied by its respective probabilities. And in this case, it gives you the value 3. Okay, so what is the average value? 3 for this case. Another word for this average value is called expectation. Meaning to say, if I were to do this same experiment in the future, we would expect a nominal value of 3 to occur. And this multiplication of probability to the random variable actually is very logical. 1 is multiplied by 0.1 because it has a 0.1 chance of occurrence. 2 is multiplied by 0.2, 3 is multiplied by 0.3, 4 is multiplied by 0.4. Add it all up, it gives you what is the most expected value out of everything. Okay, so let's derive the general formula. So in this case, we have the expectation. So following what we have done there is actually 1 times p x equals to 1 plus 2 times p x equals to 2 plus 3 times p x equals to 3 plus 4 times p x equals to 4. Okay, again, we'll simplify it with the summation sign. So the sum of it will be xi times p x equals to xi. So the expectation or the average value can simply be calculated by the sum of all individual random variable multiplied by its own probabilities. Okay. Okay, next, how about variance? So the variance, okay, as I mentioned, okay, it's actually the how much does each of my data deviate from the average value. So how do I calculate it? If you look at the numerical formula here based on the example, okay, for the random variable 1, I will subtract it by 3 because 3 is the average value, correct? So 1 minus 3, I will square it and multiply by the respective probability. Next, plus 2 minus 3 times the respective probability. Next, 3 minus 3 square times the respective probability. And for the last variable, it will be 4 minus 3 times 0.4 is equals to 1. So this formula, again, very logical. We are using individual values of your random variable, subtract it by the mean value. The reason we square it because some data will be more than the mean value. Some data will be less than the mean value. So we square it to achieve an all positive equation. And you multiply it by the probability and you sum it up. So just now I also mentioned before the standard deviation. So the standard deviation is basically the square root of the variance, which is given by sigma. So remember, variance is sigma square, standard deviation is sigma. In this case, it's still going to be the value 1. So how do we derive the general formula for variance? So again, we are going to use back what we have done there. So the variance of x, okay, will be 1 minus the average value, which is the expectation, square times p x equals to 1 plus 1, sorry, not 1, plus 2 minus expectation square times p x equals to 2 plus 3 minus e x square times px equals to 3. Okay, I'm not going to write the last term. You know what it's going to be. 4 minus expectation square times px equals to 4. Okay, so you see, every term we will use the random variable minus away the expectation. Okay, again, very logical because we want to know how much deviation every term is from the norm. So in this case, we can write down the general formula using a summation sign. It will be xi minus away the expected value square times p x is equals to xi. Okay, so this is it for the variance. Okay, so we can choose to use this, or there's another equation that we can use. So we can derive the second equation. Okay, so from what we have done, from here we'll continue. Okay, we'll continue derivation. Okay, so what I'm going to do is expand the bracket. So it'll be xi square minus 2xi expectation plus expectation square. I'll put a square here. Times p x is equals to xi. Okay, so we can break it apart using the summation property. We can split everything up. So the first term will be xi square times px is equals to xi minus away. Okay, the next term will be the sum of 2xi ex times px equals to xi plus sum of e square x px equals to xi. Okay, so we are going to do some simplification. So for the first term here, okay, the first term here, okay, this is actually the expectation of x squared. How do we know that? We can actually compare this formula here with whatever that we have here. So if I want to find the expectation of x, it will just be the x term multiplied by the probability. On the other hand, if I want to find the expectation of x squared, it will be the sum of x squared times the probability. Okay, so we'll replace the first term with ex squared. For the second term, okay, let's take out the constant. 2ex is a constant. Sum of xi, px is equal to xi. Why can I take out 2ex? Because 2 is a constant, ex is also constant because ex is the average value. Okay, so we can take it out. Plus, going to do the same, we can take out the e square x times sum of px equals to xi. Again, we can take out the e square x because it is a constant. So with that, ex square minus away. So the second term, what is this? What is my p summation of x px equals to xi? This is your ex. So this will be 2ex. So therefore, this will be 2e square x. Okay, followed by the last term. The last term, what is the sum of the all probabilities? This is actually equals to 1. So the last term here will just be e square x. Okay, so that's it. We can simplify it and you will get ex square minus away. Okay, let me just put a bit. Ex square. Okay, so this will be my alternate expression. Ex square minus away ex whole thing square. So when you calculate variance, we can choose to work directly with the data, okay, by using individual data minus the average value square times the probability, then sum it up. Or we can calculate ex square and ex, then after that apply the formula. Again, ex square is given by this formula here. All right, so that's it for the variance. Okay, so before we move into the question, okay, a few properties that we need to talk about, okay, for variance and expectation. Okay, it's seen up here. Okay, so for the expectation, so if we were to compute the expectation of ax plus b, whereby a and b is a constant, okay, the properties of expectation is such that we can take out all the constant. So it's a times ex plus b. Okay, can. Next, if I were to find out the variance, okay, of two random variables, x1 and x2, okay, then the result will be variance of x1 plus variance of x2. So irregardless of whether is it plus or minus, variance can only add. I say again, irregardless of plus or minus, the variance will only add. And then the last property, okay, if I were to calculate the variance of ax plus minus b, all right, so if I have a multiple in front of the x, so in this case, you can see I have a multiple in front of the x. Oops. Just adjust it. Okay, so I have the multiple in front of the x, correct? The a value, correct? The a value. Oops. Okay, so if I have the multiple in front of the x, so once I have the multiple, I need to square it. So it will be a squared times variance of x. How about the plus minus b behind? So variance is not like expectation, because variance, we are looking at the difference between the data value and the mean. So any constant value that you add or subtract to an expression will not affect. Because if you add b to one data, you add b to every data. So there's no change in the variance, because the variance is the difference. If you minus b from one data, you'll minus b from all data. So again, there's no difference. Okay, so if it is a var ax plus minus b, is only a squared var x. Okay, good. So now we will come into the first practice question. Okay, so we have a discrete random variable x given by this probability distribution table. So A, show k equals to 0.1. Okay, so what we are going to do here, very simple. We are just going to apply whatever that we have learned. Okay, so based on what we have learned, the sum of all probabilities must be equals to 1. So k plus 2k plus 3k plus 4k must give you 1. So therefore, k is simply 0.1. Simple. Okay, this is just a very elementary question. Expectation of x. So the expectation of x, how do we find it? Okay, you will use the individual value multiplied by the probability. So it will be 1 times k plus 2 times 2k plus 3 times 3k plus 4 times 4k. And the expectation in this case will give you 3. C. How do we get the expectation of x squared? So as I mentioned, if the expression is squared, we'll just follow. So it will be 1 square times 0.1 plus 2 square times 0.2 plus 3 square times 0.3 plus 4 square times 0.4. And the expectation of x squared will give you 10. Okay, so for D, okay, before we can compute the augmented equation here, let's find out our var x first. So var x, we're going to use the equation that we have derived just now, which is expectation of x squared minus expectation of x squared. So in this case, will be 10 minus 3 squared, which is 1. Okay. So if you were to compute our var 2 minus 5x, okay, can, so as I mentioned, because it's variance, so we don't need to care about the 2. All right. So you'll just be minus 5 squared times var x. Okay, which is 25 times 1, which gives you 25. Okay, so simple. All right. Okay, next, let's move on to E. Okay, so for E, we have to show that x1 plus x2 equals to 4. So what is this x1 plus x2? x1 and x2 are basically 2 instances of an experiment. x1 and x2 are different from one another because it's 2 different occasions whereby you are doing this experiment. So x1 can be 1, 2, 3, 4, and x2 can also be 1, 2, 3, 4. So that means to say, what are they asking for? X1 plus x2 is equals to 4. How do we get x1 plus x2 equals to 4? So we need to go and look at the possible combination. So the possible combination we can have here is when x1 can be 1 and x2 can be 3. 1 plus 3 equals to 4. Okay, you can flip them around. So multiply by 2 plus p x1 is equals to 2 and x2 is equals to 2. In this case, you don't need to flip them around because they're identical. Okay, so what is px equals to 1 times px? What is px equals to 1 and px equals to 3? Because they are independent. Remember, the last lesson we said if two probabilities are independent, we can simply multiply them together. So x equals to 1 is 0.1 times x equals to 3 is 0.3 times 2 plus x equals to 2 is 0.2 times x equals to 2 is 0.2. So this value here will give you your 0.1 that they are looking for. Okay, so with that, F, we are asked to compute the distribution table for x1 plus x2. Okay, so they have done up 2, 3, 4, 6, and 7 for me. So I just need to do 5. So how can I make x1 plus x2 equals to 5? What are my combinations? Okay, so x1 plus x2 equals to 5. Okay, if we do it the same way, all right, it will be 1 and 4. So px equals to 1 times px equals to 4, flip around, plus px equals to 2 times px equals to 3, flip around. Add together, this will give you 0.2. Next, how do I get px1 plus x2 equals to 8? Okay, so in this case, there's only one scenario whereby you get 2 4s. So it will be px equals to 4 times px equals to 4, which in this case is 0.16. All right, so we have completed the table. You can do a double check, add everything up together. It should give you the value 1. The sum must give you 1. So find the probability of x1 plus x2 between 1.5 and 3.5. So between 1.5 and 3.5. So the values that we need is 2 and 3. So the answer, very simple, is 0.01 plus 0.04, which is 0.05. All right, so that's it for the first example. Okay. Okay, the next example. Let me just put my marker. Okay, so for the next example, okay, we have a fair blue dice. All right, so the outcomes is as follows. All right, so we are supposed to write down the probability distribution for B. So what they are asking for is to summarize the table for them. Okay, so very simple. A, the table, okay, will just have 3 outcomes, 1, 3, and 5. So this is given by B. Okay, so PB is equals to BI. So how many 1 occur? So this is actually actual data. So what is the probability of getting 1? So you need to count the number of times it occur. It occur 2 out of 6 times. Same thing. how many times 3 occur? 2. 2 out of 6 times or so. So the probability translates accordingly. And 5 also 2 out of 6 times. So this is what we call an uniform distribution. Okay. So the expectation of B, very simple. We'll just use 1 times 2 out of 6 plus 3 times 2 out of 6 plus 5 times 2 out of 6. Okay, so add it up together. This will give me 3. That's my expectation. Okay, next, the second die, which is a red one. Let me use a red colored ink. Represented by the random variable R. Okay, the distribution table is given as this. So for D, expectation of R will be 2 times 2 over 3 plus 4 times 1 over 6 plus 6 times 1 over 6. Okay, so this will give you your expectation of R, which is 3 also. Okay, so for var R, okay, there's 2 ways you can do it. Either you can work out with the actual data. Okay, so just now I've used the formula. Now let me try to use the actual data. So it will be 2 minus 3 square times 2 over 3 plus 4 minus 3 square times 1 over 6 plus 6 minus 3 square times 1 over 6. Okay, so this is the other form 1 of the variance formula. Okay, so in this case, if you add them up, it will give you your variance of 2 and 1/3. Okay, next we have part F. So we have these two guys that is inviting people to play the game. Tom invite Avisha to play a game. So Tom spins a fair coin with one side labeled 2 and the other side labeled 5. When Avisha sees the number following, she then chooses one of the dice and roll it. If the number shown in the die is greater than the number showing on the coin, Avisha wins. If not, Tom wins. Avisha will choose the die which gives her the best chance of winning each time. Find the probability that Avisha wins the game, stating clearly which die should use in each case. Okay, so in this case, we can use a simple tree diagram to represent the scenario. So again, tree diagram, remember I said last week, you should label the two entities first. So in this case, it's Tom and Avisha. So Tom is going to do the coin, okay, which either he get 2 or he's going to get 5. Probability of getting 2 is half. Probability of getting 5 is also half because it's a fair coin. Okay, so for Avisha to win the game, okay, there's two choices. He can choose the blue die or the red die. So if he choose the blue die, he must get a 3 or he must get a 5. Okay, on the other hand, okay, let me just branch out one more. If he choose the red die, all right, he should get red is equals to 4 and red is equals to 6. All right, the probabilities are different for each case. Okay, so this will be 1/3, 1/3. This will be 1 out of 6, 1 out of 6. Okay, so the probability for the first case will be 1/2 times 1/3 is 1/6. This one also 1/6. This one will be 1 over 12. This one also 1 over 12. Okay, so if you choose the blue die, the probability here will be 2 out of 6, which is 1 out of 3. Second die will be 2 out of 12, which is 1 out of 6. So clearly, the blue die is better. Okay, followed by for the 5. Okay, so if the coin goes 5, okay, he can only choose the red coin, and the red coin will give you 6 if he has to win. So it's 1 of 6. So this will be 1 out of 12. Okay, so the total probability of winning will be 1 out of 3 plus 1 out of 12. Okay, so which is 5 out of 12. Okay, and provided that he must choose the blue die. All right, okay, so that's it for this second example. Right, let's move on. Okay, so the second part here, okay, we will try to interpret the results and try to fit into existing probabilistic model. So what is this model we are talking about? So just now at the beginning, I got mentioned that we are interested in a few models for this H2. Okay, so it's either we use the uniform distribution model, binomial model, or normal distribution model. Okay, normal distribution model, I think most of us know, is actually a bell curve. Later we look at it. So these models are just a mathematical function to calculate the probability. Okay, just a mathematical equation. This equation, okay, in our context, we will call it the PDF, or the probability distribution function. So instead of just looking at the raw data in the table, if somehow we manage to fit it into a mathematical model, we can use the function itself to calculate the probability. Okay, can? So nothing much to say. We can proceed with the example over here because the concepts are still the same. Okay, so if I have a discrete random variable x with a PDF of this, show that k equals to 1 over 18. So same thing, all probabilities must add up to be 1. So in this case, px equals to 2 plus px equals to 4 plus px equals to 6 plus px equals to 8 must give you 1. So px equals to 2, I must use the first one. 2, 4, 6, I must use the first one. So it will be 2k plus 4k plus 6k. X equals to 8, I must use the second one accordingly. Okay, so this will be plus 6k. All right. So in this case, if I add everything together, this will be 18k equals to 1. So k equals to 1 over 18. Okay, so everything is as per normal, but instead of looking at the raw data, we can use the formula to compute the probability. Okay, can? Okay, so B is something new. B, what we are looking at is big F. What is big F? Big F is actually what we call the cumulative distribution function. Cumulative means it accumulates whatever that is less than the value shown here. So for this case, F5, everything less than 5 will be Px equals to 2 plus Px equals to 4. Anything else? Nothing else. So the cumulative up to this value. Okay, the cumulative up to this value. So we are going to add them up together. In this case, it will be 2 out of 18 plus 4 out of 18. Okay, if you wanted. Okay, can easy. Next, for C, find the exact value of the expectation. So same thing, expectation will be used the random variable itself multiplied by the probability. So this will be 2 times 2 over 18, okay, plus 4 times 4 over 18, plus 6 times 6 over 18, plus 8 times 6 over 18. Add them up together, this will give you 5, 7 over 9. Okay, can? Good. Okay, next, C, expectation of x squared. So it's the same thing, just square the variable itself. So it's 2 square times 2 over 18 plus 4 square times 4 over 18 plus 6 square times 6 over 18 plus 8 square times 6 over 18. Add them up together, this will give you 37 1/3. Okay, so since I have this D, sorry. Since I have everything here, for E, I can calculate the var x by using the formula of expectation of x squared minus expectation of x squared. Okay, so expectation of x squared is from D, which is 37 1/3, minus away from C, okay, which is 5 out of 7 over 9 square. Let's do it. This will be 3.95. Okay, so to get the var 3 minus 4x, so again, this 3 can be ignored because it's variance. All right, so this will be minus 4 square times my var x. Okay, so let me just calculate it. This will be 16 times 3.95. This will be 63.2. All right. Okay, Ken. So everything is the same. The formula is the same. It's just that instead of presenting in raw data, I give it in terms of a function. Okay. Okay, good. So the next example, okay, we are going to look a bit more into the cumulative distribution function. Okay, just in case it comes up for the exam. So if let's say they don't give us the PDF, they give us the CDF instead. Okay, in short, we can call this CDF, cumulative distribution function. So how can we work with this? So concept is the same. Part A, how do we show that k equals to 13? Okay, so x today is either 1, 2, or 3. So actually, can you see that F3, as I say, cumulative distribution function is the sum of up to that value. So this is actually P x equals to 1 plus P x equals to 2 plus P x equals to 3. This gives you 1. Okay, so this itself, but we don't have to work with all this because we already have the equation. So this is 3 plus k over 40 is equals to 1. Simplify this and you get k equals to 13. Okay, good. So how do we then find the distribution of x? Okay, so we can actually compute them individually. So F3, we know that it's equals to 1. F3 was x equals to 1 plus x equals to 2 plus x equals to 3. How about F2? F2, if I sub into the formula, okay, will be 2 cubed plus 13 over 40. Okay, so this value is 21 over 40. And this here will be P x equals to 1 plus P x equals to 2 because it's up to that value. Okay, so in fact, you can see that if I use this minus this, I will get my Px equals to 3. Correct? In this case, Px equals to 3. If I use 1 minus 21 over 40, this is actually 19 over 40. How about F1? F1 will be 1 cubed plus 13 over 40. And this here will give you 14 over 40. X1, F1 is just x equals to 1. So I have with me Px equals to 3 Px equals to 1. So therefore, 1 minus all these values will give me Px equals to 2. Okay, so this will give me my 7 over 40. That's it. Okay, you can put this all this into a table and then present it. All right. For this case, I'll not go through part C because it's the same thing. Okay, Ken? So this is how you work with the CDF. Okay, let's move on. Okay, let's look at this example over here. This is the last example. Yeah, this is the last example. Okay, so this is more of an application question. So if let's say I have a insurance company. Okay, from the past records, the number of days the hospitalization for an individual with minor ailment can be modeled by a DRV with a probability density function of this. So in this case, X can be 1, 2, 3, 4, 5. So this represents the number of days. Okay, so the rest is otherwise. That means it's not possible to stay more than 5 days. This doesn't really apply for the COVID situation. Okay, so the insurance pays $100 per day for 3 days. Okay, up to 3 days, and $25 per day thereafter. All right. We are just going to do part 1. We are not going to do part 2. Part 2 is not. We cannot do it yet. Okay, we need to go on further to be able to do this. So part 1, calculate the expected payment for the hospitalization for an individual under this policy. Okay, so how do I calculate this? Okay, sorry, okay, so first of all, what we can do is to come up with the distribution table. Okay, so for the distribution table, okay, currently we have 5 columns, 1, 2, 3, 4, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. All right, so if it is 1, okay, this will be 6 minus 1 over 15. 6 minus 1 over 15, what's my value? Just give me a minute. 6 minus 1 over 15 will give me 5 over 15. So this will be 1/3. 6 minus 2 over 15 will give me 4 over 15. 6 minus 3 over 15 will give me 3 over 15. So it's 1/5. 6 minus 4 over 15 will give me 2 over 15. And then 6 minus 5 over 15 will give me 1 over 15. Okay, so this is my probability. Okay, so how do I get the expected payment? How can I write down the expected payment? So we can actually come up with one more column. So instead, the last column here, we call it the payments. So 1 day, it will be $100. 2 days will be $200. 3 days will be $300. 4 days will be $325. 5 days will be $350. So these are the payments for the individual days. So what we want to know is not the expected number of days. Instead, we want to know what is the expected number of payments. So if we were to use the expectation idea, we will use $100 multiplied by 1/3 plus 200 multiplied by 4 over 15 plus 300 multiplied by 1 over 5 plus 325 multiplied by 2 over 15 plus 350 times 1 over 15. So the expected value of the payment that I'm going to receive is 3,213 and 1/3 dollars. So if today we are dealing with money, okay, we can calculate it separately, like for this case. Okay, we can calculate separately. Then after that, we can use the probability to multiply, okay, by the value, okay, instead of the random variable. And this will give us the expected payments. All right, Ken, so that's it for this question. I think I missed out one question. I'm not sure if, let me see if I include